In the previous programming screencast, we compared the myopic search with optimal search. Now next what we are interested in looking at is the time taken by the myopic search. So if I perform my myopic search on a network of, let's say, 100 nodes, what is the time taken? On a network of 200 nodes, what is the time taken? So on and so forth. Is this time linear in the number of nodes or logarithmic in the number of nodes or what? So for doing this, what we are going to do is, first of all, let's take a network having 100 nodes. So we take a network having 100 nodes as previous. So we have nodes here 0, 1, so on and so forth. And here is 99. And we are going to do the same procedure what we did before. We'll take the diametrically opposite points and look at how much time does myopic search take to work on these diametrically opposite points. So we will be taking the point, let's say 0, 49, and then we'll see the time taken by the myopic search. Then for 1, 50, what is the time taken? For 2, 51, what is the time taken? So on and so forth till 50, 99, what is the time taken? Now what we'll do next is we'll take the average across all these times. That will give us on an average, if we take two diametrically opposite points on this network, on an average what is the time taken by the myopic search. So we calculate the average here. Now this we have done for a network having 100 nodes. Next what we'll do, we'll repeat the same procedure on a network having 200 nodes. So we'll be taking a network having 200 nodes. So it will go from 0 to 199, and then we'll again take the diametrically opposite points, which here will be let's say 0, 99 and then 1, 100, so on and so forth. And again we will take the average here, and that will give us the time taken by myopic search on this network. Okay, while doing this, we also take care of a small thing. So when we have a ring network over here, right? So I've shown you here the homophily based links, and we know that there are going to be some weak ties as well. So previously in this network, we have taken 10 weak ties, right? We have taken 10 weak ties. Now, if this network is big, right? So what we will be going to assume in our programming screencast is that the number of weak ties is 10% of the number of nodes in the network. So for here we have 10 weak ties. Here we will be making 20 weak ties. In the next network, which will be having 300 nodes, we will be having 30 weak ties, so on and so forth. And then we'll do this process and we'll find the average over here, and at the end what we will be plotting is, on the x-axis we will be plotting the size of the network, that is the number of nodes in the network, 100, 200, so on and so forth, let's say up to 1000. And on the y-axis we will be plotting the average we have calculated. So what is this average? It tells us that for one particular network, if we take the diametrically opposite points on this network, so if we take these diametrically opposite points on this network, what is the average time taken by our myopic search? And we'll look at how does this plot look like. Is it linear? Is it logarithmic? Or what? So next what we want to do is, now we want to find out the time complexity of myopic search, time which our myopic search takes for different size of networks. So till now we have considered only one network which was having 100 nodes. Now we are going to do an experiment. We are going to build small world networks of different sizes, 100, 200, 300 up to 1000, and we'll do a myopic search there, and we'll see that how much time on an average does this take. So at the end we want a plot where on the x-axis is the number of nodes and on the y-axis is the average time taken by my myopic search. So I make some arrays here. So I make an array x1 for the x-axis, which will be my number of nodes, and an array y1 for the y-axis, which will be the time which my myopic search is taking. And what I have to do is, Now I have to create networks of different size and do this entire process for all these networks. So I have to basically put all this code in a loop. So what I'm going to do is for numin, and I'm going to take a list here consisting of the values 100, 200, 300, 400, 500, 6, so up to 1000. And then what I'm going to do is, the graph I'm going to create here is going to be from range 0 to num. So first of all, I'll get a network on 100 nodes, then 200 nodes, so on and so forth. And I'll put everything inside this loop. And now here one thing to be noticed is T here, it is telling us the number of weak ties which we have to add. So the number of weak ties should change according to the number of nodes in the network. So instead of 10, what I am going to do here is, I am going to make it here, while T is less than or equals to G dot number of nodes divided by 10. That is, I am going to have 10% of the edges in a network to be weak ties. So whatever are the number of nodes in the network, so if there are 100 nodes, number of nodes. So if there are 100 nodes, I'll be having 10 weak ties. If there are 200 nodes, I'll be having 20 weak ties, so on and so forth. And then I'm going to add these long range links, and rest of the things remains the same. Okay. Now my this value u will range not from 0 to 49, it will range from 0 to G dot number of nodes divided by 2, right? 0 to G dot number of nodes divided by 2 and minus 1, and v is going to be u plus G dot number of nodes divided by 2. And then we are going to apply a myopic search here, find out the path. We are not doing an optimal search over here. And then, okay, m dot append length of p. M here is an array. So as you can see that m is an array over here, which holds the path length corresponding to the myopic search. So you see what is happening over here. For some small world network here, we are performing a myopic search. So we have a small world network. We have done this myopic search, and we do it for many pairs of nodes. And at the end, what we want to append to our y-axis is nothing but the average of everything. So what is going to come in our y-axis is, when we come out of this loop, what we are going to append in our y-axis is the average, which is np dot average. Np is numpy dot average of m, right? And what is going to be coming across x-axis is nothing but the number of nodes, G dot number of nodes. And at the end, what will we be plotting is x1 against y1. So I hope that this code is clear. What we have done is, I'll quickly recap it. So here are my two arrays x1 and y1, where x1 is the different, so x1 is nothing but this thing here. This complete will be x1, which is the number of nodes in different networks, and y1 will hold the average path length which myopic search takes to connect our diametrically opposite points. And then we make this small world network. After making this small world network, we take an array M here, and then we perform this myopic search for all the diametrically opposite points and keep appending the path lengths in this array M, and at the end we take the average of this M and append it in Y1, and this average of this M we append in Y1, and X1 has nothing but the number of nodes. And we have used the module numpy, so that needs to be imported. So I import numpy as np. Let's execute and see it. So it will take some time. For the sake of clarity whether our code is running correctly or not, what we are going to do is, where is my first print statement? We'll remove that print. Okay. We do not print the list of nodes here. Instead, what we do here, whatever we are appending, we print here. So we print here whatever we have appended in the x-axis, g dot number of nodes, and we print here and p dot average of M. See now. Okay, so when our network was consisting of 100 nodes, it took 13 steps, 200 nodes 19 steps, so on and so forth. Give it time to run and let's see the final output. And you can actually do this process for more number of nodes. So in your code, instead of 100, 200, 300, you can take 100, 150, 200, 250 to get more data points and have a better plot. Okay, so here is the plot, and what if you plot it for more data points, you'll see the plot more clear, and you can actually observe that this is not a linear plot, rather it's a log plot. So as you increase the number of nodes, the time which myopic search takes to execute increases logarithmically, not linearly.